Concept getters, how are you? I hope everything is going well and that you guys are preparing for June exams efficiently, effectively, and productively, and that you're going to ace them. All right. So in this particular video, I'm introducing all the theorems for grade 11 and 12. But if you are in grade 11 and you get to the part where you realize that I'm starting with the grade 12 concepts, you can stop and get out of here. All right. But if you're curious, just watch the whole video. There's no harm in that. But otherwise, I'm going to go straight to the first theorem in grade 11. In grade 11, the first theorem is this one, right? I'm going to draw, never mind my handwriting and my drawings. I'm not an artist. So I'm just going to draw, right, the way I have to, the way I can. The most important thing, remember, is concept. It's the concept. Since you're a concept getter, just get the concept, okay? So the first theorem says, it says that the line drawn from the center, let me draw it, the line drawn from the center of a circle, and that line is perpendicular to the chord. Perpendicular meaning they intersect at an angle of 90 degrees. This here is your chord AB. And the line drawn from center is this one. Since your, not A, I mean O. Since your center is O. If a line is drawn from O, right, and it intersects with AB, which is your chord, at an angle of 90 degrees, which is perpendicular to the chord, it will bisect the chord. The result is it will bisect the chord, meaning A, let's say here we have C. AC will be equal to CB. To bisect means to cut something into two equal halves, right? So this theorem states that we have AC is equal to CB if OC is perpendicular to AB. Clear? That's the theorem. I'm just explaining the theorem, right? Also, before I even go to the second theorem, because sometimes they also introduce it like this. You don't only start with line drawn from center is perpendicular to the chord and therefore bisects the chord. No, you can also say the perpendicular bisector of a chord passes through the center of the circle. Does that make sense, guys? Let me say it again. If you have a line which is a chord and there's another line here which is perpendicular to the chord, that's why it's called a perpendicular bisector of a chord, right? It's perpendicular, and bisector means it cuts the chord into two equal halves. That line has to pass through the center of a circle, meaning it's going to be a line drawn from center. Does it make sense? So every time when you have a line which is perpendicular to the chord and it also bisects the chord, that line goes to the center. Always. And then we go to the second theorem, right? Let's leave this one. We go to the second one. Let me clean this one up a bit. Juju. And then we go to the second one. The second theorem says the angle subtended by an arc. Let me draw it so that you see. We have center here. We can call it O. And then I will draw this boom boo. And then I will say voo boo. Right? Don't mind my drawings. Remember, I'm not an artist. Here we have A, B, and C, right? The theorem states that the angle subtended by an arc at the center of a circle is double the size of the angle subtended by the same arc at the circle. So look at it. This is the center here, right? This is an angle at the center. Remember, our O is the center. And then there's an angle at the circumference here. Now, let's look at BC. BC is an arc. An arc is a curve, right? Is a curve that has a starting point and an ending point. We have arc BC. Arc BC subtends angle O at the center. To subtend means to be opposite to. And also, arc BC also subtends angle A at the circumference. If there's an arc, that same arc subtends two angles, the one in the center and the one at the circumference. Those two angles will have a relationship. What is the relationship, Mr. Say? The one in the center, the angle in the center will be twice or will be double the size of the angle at the circumference, which means our angle O will be equal to 2 times angle A. When you apply it, you say if angle O is 30 degrees, therefore angle A will be 15 degrees, so that 2 times 15 can give me 30. Therefore, the angle at the circumference should be half of the angle at the center. Or you can say the angle at the center is twice the angle at the circumference. Does it make sense, guys? I hope it makes sense, right? So now we go to the next theorem. I'm just introducing these theorems, right? To the next theorem. The next theorem says that angles subtended by a chord of the circle on the same side of the chord are equal. This one is easy, guys. Let me show you in a drawing. If you have a chord, remember now we're no longer talking about an arc, right? We're saying angles, right, subtended by a chord of the circle on the same side of the chord are equal. Those angles have to be on the circumference. So let me draw it. You have this. So if I have an angle at the circumference here, right, and I draw another one at the circumference here, do you see them? They all come from the same chord. This chord subtends this angle, and the same chord subtends this angle here. So these two angles at the circumference will be equal. If this one is 20, this one is also 20. Remember, they have to be on the same side of the chord, on this side of the chord. Because if they were on either side of the chord, imagine if we have this one and we have this one here. This is one angle, this is one angle, this is the chord. If they are on either side of the chord, they can never be equal. They have to be on the same side. Does it make sense? This is how this theorem works. So we call these angles. When we call them, we say angles in the same segment. I don't know if you guys are familiar with this. We say they are angles in the same segment. Let me say A, B. We're going to say A is equal to B. We say they are angles in the same segment. Angles in the same segment, right? This one we're going to say angle at center equals to 2 times angle at circumference. This one is perpendicular bisector of a chord. Perpendicular bisector of chord, right? Or line drawn from center. Or you can say line drawn from center. Clear? So when we go to the next one now, remember guys, I'm just introducing the theorems, right? I'm just introducing the theorems. The next video is going to be based on applying all these theorems all together in riders. So the next one says the opposite angles of a cyclic chord are supplementary. This is my favorite one. You guys know, you guys should know by now. This is my favorite one. This one says when you have something of this kind, and I draw this, and I draw this, and I want to come back to this later, but let's just do this. I draw this, and I draw this. They say the opposite angles, this angle and this angles are opposite to each other, right? Do we agree? And also, this angle and this angle are also opposite to each other. So they say opposite angles of a cyclic chord. What is a cyclic chord? A cyclic chord is a quadrilateral. A quadrilateral is what is a shape of 4 sides and 4 vertices. So a cyclic chord is a quadrilateral whose vertices are at the circumference of a circle. So if one of the vertices is not on the circumference, therefore it is not a cyclic chord. So now let's start with the theorem. They say the opposite angles of a cyclic chord, basically the opposite angles of a quadrilateral whose vertices are on the circumference of a circle. The opposite angles found in that shape, they do what? They are supplementary. What is supplementary? Supplementary means they add up to 180. When you have x plus y is equals to 180, it means x and y are supplementary. Do that make sense? So if you have A, B, C, and D, we can say A plus C is equals to 180, or we can say B plus D is equals to 180. The reason is what? Opposite angles of cyclic or in cyclic chord. They are always supplementary, meaning they add up to 180. When you apply it, you say, if here I had 50 degrees, which means here I have 130. Why? Because 50 plus 130, when you add them, they give you 180. That's how you apply. So if they give you C, you can get A. If they gave you D, you can get B. Do that make sense? That's how you apply it. So we go to the next one now, right? Since you understand this one, you go to the next one. But wait, before we go to the next one, because I'm overexcited, I want to explain something. Remember, I was explaining that this is angles in the same segment. Remember, when we talk about angles in the same segment, what are we talking about? When you have a circle, right, and you draw a chord, this chord divides the circle into segments. This is a big segment, this is a small segment. And I mentioned that they have to be on the same side of the chord, meaning they have to be in one segment. So these angles here, look at this diagram, these angles here are subtended by this chord on the same side of the chord, meaning on the same segment. Do that make sense? Because if they were on either side of the chord, they will be on different segments. So they have to be in the same segment, and they have to be subtended by that chord or the same chord for them to be equal. So that's why the theorem states that these are angles in the same segment. I wanted that to be understood by all the concept getters, by the way. It's very thrilling to see concept getters going, you know. Otherwise, we move into the next one, right? The next one now is they're talking about an exterior angle of what? Of a cyclic quad. Guys, concept getters, don't tell me you don't know this one or you don't like this one. Let me draw something like this. We have a cyclic quadrilateral here, and it goes like this. And they say, remember, let's talk about exterior. When I have a triangle and I want an exterior angle, there should be an extended side so that we can have an exterior angle. So even when it comes to a quadrilateral, when I want an extended angle, there should be when I want an exterior angle, there should be an extended side. When I extend the side, I have an exterior angle. When I extend the side, I have an exterior angle. When I extend one side, I have an exterior angle. The minute I just have a line, just lying, this one is not an exterior angle. An exterior angle is a result of an extended side. Clear? So now, when you talk about an exterior angle of a cyclic quad, we're talking about an angle formed by an extended side on that cyclic quad. So let's look at this quadrilateral. When I extend it, I will have an exterior angle. And the theorem states that this exterior angle of a cyclic quad is equal to an interior opposite angle, this one. So you go in which, then you go opposite, and it's going to be this one. So that's the theorem. Clear? So if this angle is A here and this one is X, this theorem states that X is equal to A. Right? The reason is you just say exterior angle of cyclic quad. And you go like that and you go boom, you're done with the theorem. Clear? So all the time. So if this one was 30 degrees, this one was also going to be 30 degrees. Doesn't matter where. As long as it's a cyclic quad and there's an extended side, you have an exterior angle. And that exterior angle is going to be equal to the interior opposite angle. This is easy, ne? Then we go to the next one, right? This one is also, when we go, these ones are my favorite. My favorite ones are the ones that have tangents. I love tangents. I'm sorry, I love tangents. So let's start with the first one, right? And I proved this one. It's also one of my most viewed ones because I simplified it like nobody's business, That's if nobody has a business. But yeah, let's look at this one. When we have a triangle nyana in here, right? And we have a tangent. Guess what mathematics says? Mathematics says that when you have an angle outside, that angle is formed by one of the chords and the tangent. A tangent, remember, is a line that touches a curve at one point. So when a chord and a tangent intersect at one point on the circumference of the circle, they will form an angle outside. That angle will be equal to what? An angle in the alternate segment. I explained this one when I was proving it. You can check, just go straight to my playlist. Go to the playlist on this channel, go scroll down to Euclidean geometry, and then look for this particular theorem. You'll understand it. So it says when we have an angle here, which is A, it will be equal to this one. Guess what? This angle is formed by the chord and the tangent. That very same chord that forms the angle outside should subtend an angle inside in order to know which one will be equal to it. So the one subtended by the chord will be equal to the one made by the chord outside, made by the chord and the tangent outside. So this theorem states that an angle formed by a chord and a tangent, right, will be equal to an angle in the alternate segment. Alternate segment means it is subtended by the very same chord in another segment. Come on, guys. Come on. Don't tell me this is not easy now. So we know that if you have A here, you also have A here. If this is 30 degrees, this will also be 30 degrees. And the reason is what? Tan-chord theorem. So you can call it Tan-chord theorem. Clear? And there's another one. This one is simple. Everybody knows this one. You can just call it a radius and a tangent. They always intersect and at an angle of 90 degrees, right? So we call it what? Tan perpendicular to radius. So always a radius and a tangent at the circumference, at the point of contact with the circumference, they will always intersect at 90 degrees, always. And there's another one again, which is interesting, guys. It says when you have, let's say I'm drawing a circle here, and I'm saying there's a tangent here, and I draw it, and there's another tangent here, and I draw it. Those two tangents, when they meet outside the circle, at the point of from the point of contact with each other to the point of contact with the circumference, the length here will be equal to the length here, so they will be equal in length. So we call them tangents outside circle. When you use this theorem for your reason, you're gonna say tangents outside circle. Come on, guys, these things are easy, né? And then there's one that I left that is very special to my heart. So I'm gonna do a bit so that I can create space for it and then go like a bit, and I'm gonna draw it here. Right? This one I love it because it's easy and it's always almost there. So let's draw it. When you have a diameter, what is a diameter? It's a straight line that passes through the center, and it starts at one point on the circumference and ends on another point on the circumference on another side, but it passes through the center. That's very important. So a diameter will always, will always subtend a 90 degree at the circumference all the time. This diameter will always subtend a 90 degree at the circumference. Why? This is a result of this theorem, right? Look at it. Why? Because when you have a 180 here, angle at center subtended by this arc, this is 180. It will be twice the angle at the circumference as well. So if you have 180, half of 180 is 90. So it will always be 90. Do you see it? The angle at center on a diameter is 180 because the angle on a straight line is always 180. Now, if the angle at the center is 180, what about the angle at the circumference if they are subtended by the same arc? It will be half of 180, which is 90. So it comes from second theorem. That's why I love it. It's easy. Every time when you see a diameter, just think of 90 degree at the circumference. Every time when you see a radius and a tangent, this one here, just think of 90 degree at the point of contact. Clear? And all other angles depend on their relationships. Come on, guys. Don't tell me this is not easy. Don't tell me this is not easy. Anyway, I don't want to apply them on a question or on a rider. I'm just going to do riders on other videos. But let's go to grade 12. Concept getters, if you are in grade 11, you can stop here. But if you are in grade 12, let's move. Now I'm talking to the seniors in grade 12, right? There is the first theorem in grade 12, which is this one. I already proved it as well. It's very simple. So it goes like this. And it says what? It says when there is a line, right? When there is a line inside this triangle, and that line is parallel to the third side of a triangle. Remember, this is one side, two, and the third, right? So if this one is the third and there's a line inside, it's parallel to the third side, right, of that triangle. that line will cut the other two sides in equal proportion. Meaning if I have AB here, CD here, proportion meaning the ratio this side will be equal to the ratio this side. So that means if I have A, B, C, D, and E, right? This theorem states that AD over AB will be equal to AE over EC. That's what this theorem is saying. It cuts the other two sides in equal proportion, meaning the ratio or the fraction on the other side will be equal to the fraction on the other side. You can also say AD over AB equals to AE over EC. Oh, that's what I already said. What did I say EC? Actually, I made a mistake. I'm sorry. Vutu and Vutu here, right? It's A. So, or you can also say AD over DB is equal to AE over EC. Clear? Or you can say EC over AC. You know, by the way, we'll see it when we deal with the riders. But that's what this theorem is basically saying to you. It says they will be cut in equal proportion. That's the first theorem in grade 12. Now let's go to the second theorem in grade 12, right? In the second theorem in grade 12, it talks about similarity. I love this. Similarity, right? Similarity says when you have one triangle and another triangle, and those triangles have equal angles. Let's say I have A, B, C, D, E, and F. If A is equal to E, and then B is equal to D, and your F is equal to C, right? If the angles in one triangle are equal to the angles in another triangle, those two triangles are similar. And therefore, after we have concluded that they are similar, we also say, therefore, they do what? Their sides are in proportion. Clear? So let me show you now. The minute we can conclude that A is equal to E, and we also conclude that B is equal to D, and we also conclude that C is equal to F. Look, ABC, this side is EDF. We can conclude and say triangle ABC is similar to triangle EDF. And look at the arrangement, ABC. We also go with the same arrangement on the other side, EDF. Clear? So the minute we conclude that they are similar, we also say they are in equal proportion. Proportion meaning AB, you see this AB? We also have BC and we also have AC, right? We're going to take the sides of the triangle, we're going to say over the sides of this triangle. Let me show you the proportion. We're going to say AB, and we're going to say BC, and we're going to say AC. We say over, equal to equal to. This is the proportion, meaning one side of the triangle over the other, equal to another side of the triangle equal to over the other. Or you get my point. So let's see. We're going to say AB. We say small. So there's this system. I think I got it from one of the students or one of the teachers that I worked with in other schools or in a textbook. I don't know. It's been a while. I think 10 years ago. It says eyebrow, smile. Eyebrow, smile, this side. You also say eyebrow, smile. So I'm going to say AB, BC, AC. AB is the first eyebrow. On the other side, ED is the first eyebrow. So I'm going to have ED on this side. I'm going to say ED. BC is the second eyebrow, right? Also, DF is the second eyebrow. I write DF. Now, the smile is AC, right? Also, the other side, the smile is EF. I'm going to write EF. So this is the proportion. Remember, when the angles are equal, we can conclude that the two triangles are similar. Once you conclude that the two triangles are similar, we can also say, therefore, they are equal in proportion. That's what the similarity theorems talks about. Clear? Let's go to the next one. The next one is easy. It comes from grade 10. All you are doing this year is just proving it. It says that when we have a line, remember that line in a triangle, if it is parallel to one side of a triangle, but this time around we say, and it is also half of. So if this one is 2, This one is 4. If it is half of that other third side, we say it will cut the other two sides of the triangle equally, meaning it will bisect them. So we call this one the midpoint theorem. So if you have A, B, C, D, E, we're going to say AD is equal to DB. AE is also equal to EC. If DE is parallel to BC and it is also half of BC, we call it the midpoint theorem. Midpoint theorem. It was introduced in grade 10, of course. In grade 12, we are proving it using this one. Clear? Now there's the last one, the theorem of Pythagoras. Everybody knows this one. It is the one that yields what we call corollaries, or it proves corollaries, right? Theorem of Pythagoras, you've always known it. Or the minute you have something of this kind, we know that this squared is equal to this squared plus this squared. In grade 12, we are proving how it came about using similarity. We're going to do a video of this one. Otherwise, these are the 3 theorems that we are dealing with in grade 12. Come on, guys, don't tell me this was not easy. Remember to do what? To do this, to do this. To do what? You're going to subscribe. After subscribing, what do you also do? You share. How? You share because you want others to also pass and get the concept. And after sharing, you like. I mean, come on, you did like this, right? Come on, you did, right? And then after liking, you're going to comment. Actually answer that question in the comment section. Tell me if you really like this concept, if you really understand the concept, and if you'd like me to do more riders. And also give me the riders. Tell me which question paper, past paper that you tried from which province, if it's a junior exam that you tried and you struggled with and you want me to do. Just comment, and then I'll try to do it on the video and explain it to you. Otherwise, all the best.